We have our fourth and final chapter in our look at Alberta's Algebra number 4 outcome, specifically special products. We're going to look at the outcome, review the multiplication of binomials, introduce our special products, and then go through some examples and exercises. Our outcome. We demonstrate an understanding of the multiplication of polynomial expressions, limited to monomials, binomials, and trinomials, concretely, pictorially, and symbolically. Our review of multiplication of binomials. Binomials are polynomials with exactly two terms. Multiplication results in predictable outcomes, which sometimes follow patterns. Work out the patterns are powers of 11 sometime. 11, 121, 1331. You'll see patterns emerge there too. Let's take a look at our special products. There are two special products in binomial multiplication. Both special products have very predictable patterns in the final answer. That's why we call them special. This allows us to actually skip intermediate steps and go directly to the final answer. These are optional shortcuts. If you forget them, then you just will take the usual number of steps instead of cutting that in half. So it's a time saver, but you can always do things the long way. So when a binomial is multiplied by itself, a pattern emerges. It's a perfect square binomial. Anytime we have a plus b squared, we skip directly to the final result without any intermediate steps. So these are the intermediate steps. Fight the instinct to call this a squared plus b squared. When we work it out, we'll see why. So a plus b times a plus b, 2 terms times 2 terms is 4 terms before we simplify. A squared from a times a. We have an AB term from the outside and another BA from the inside before our B squared. In multiplication, order doesn't matter. BA is the same as AB. So this is A squared, 2AB, and B squared. So anytime you are squaring a binomial, you can square the first term, square the last term, and double what you get when you multiply them together. Don't forget the 2AB. By far, the most common error is to forget the 2AB. Now, when binomials differ by a sign, we get what we call the difference of perfect squares. So if you have a plus b times a minus b, you get a squared minus ab plus ba minus b squared. Collecting like terms, the a squared comes through. Minus ab plus ba is the same as minus ab plus ab, because order doesn't matter in multiplication. That's 0. Our negative b squared comes through. Right? That cross term is just 0. We don't write it. So if the only difference is a sign, we get a squared minus b squared. Let's apply them in examples. Let's calculate 3x plus 1 squared. Well, with our pattern, a plus b squared is a squared plus 2ab plus b squared. Our a term here is 3x. We just have to match it up. So we're going to have a 3x squared plus 2 times 3x times 1 plus 1 squared. Simplifying that, we get 9x squared, 6x plus 1. First example done. Our second, don't be fooled by the minus sign here. This is not a difference of perfect squares. This is the product of perfect squares where one of our terms just happens to be negative. Working this one out. Again, following our pattern. A is 4x. B is negative 5. So we're substituting in. Now 4x all squared gives us 16x squared. 2 times 4x times negative 5 is a negative 40x. And then negative 5 squared, that's negative 5 times itself. Negative times negative is positive. This is positive 25. There, we have expanded this perfect square. Now, this one is our difference of perfect squares. Notice with difference of perfect squares, we don't have an exponent. It's just one binomial times the other with a different sign. So our pattern here is the first term squared minus the second term squared. So 3x all squared minus 1 squared. We don't have the minus 1. That minus sign is part of our structure. It's part of the pattern. So this is 9x squared minus 1. All right. A fourth example, 2x plus 7 times 2x minus 7. So following this pattern, our a is 2x. Our b is positive 7. So 2x squared, or 2x all squared becomes 4x squared. 7 squared is 49. This expands to 4x squared minus 49. This is probably the easiest one to apply. First squared minus second squared. All right, exercises, your chance. Calculate 2x plus 1 all squared. Pause now. Take whatever time you need. Moving to the solution. This one fits our pattern again, where 2x is a and 7 is b. So this simplifies to 4x squared plus 28x plus 49. Now, 3r minus 2 squared. Pause now. Take the time you need. Moving on to the solution. This is a product of perfect squares factor, or form. Yes, we have a negative sign, but it's negative in both. That squared means we're multiplying identical terms. So our a is 3r. Our b is negative 2. We substitute, and then we simplify term by term. Exercise 3. This is now difference of perfect squares. Pause now. Take whatever time you need. All right, the solution. In this form, a is x, b is 11. So x squared minus 11 squared is x squared minus 121. Right, our fourth exercise, 6x plus 17 times 6x minus 17. Pause now. Take whatever time you need. All right, solving our difference of perfect squares. A is 6x, b is 17. It's a 36x squared minus 289. In summary, a plus b all squared is a squared plus 2ab plus b squared. A plus b times a minus b is a squared minus b squared. When these problems come up, you don't generally need to show intermediate steps. You could jump right to the final answer. If you have any questions, any other feedback, please leave them in the comments. I will do my best to respond in a timely fashion.